Good morning everyone, my name is Jakub Peschel and in this video I would like to present the topic of our research, which is discovering communities by frequent item set mining and similarity search. First, let's look on some motivation. One of the frequent type of data are network data. These are available in form of social networks, financial transactions, or communication networks. One of the typical tasks is community discovery based on interactions. Network communities can be used for improvement of recommendation systems, police investigation, or business reorganization. So our goal is to discover heavily interconnected groups of nodes with high chance that these are not being random. Now let's look at some network definitions. For our approach, we expect network in form of graph consisting of nodes and edges. We denote single nodes with small letters. In this work, we often use list of neighbors representation, but our representation slightly differs. For each node, we add the node itself into the list of neighbors. We then use this representation in the rest of our approach. In this presentation, we denote community as a big letter C, which is the subset of nodes from our network. Later in this presentation, we also use term core, which is also subset of the nodes, but it has connection to the resulting communities. We denote core with a small letter C. For our approach, we have also some restrictions for the graph. Some can be dealt with, others unfortunately cannot. We expect network to be undirected, single-edged, non-weighted, and without loops over the single nodes. Now let's talk a little bit about what are communities. Communities can be vaguely defined as a group of nodes. They are more interconnected between themselves in comparison to the rest of the graph. But the problem is that there is no generally accepted definition, precise definition. The problem of selecting communities is similar to the problem of network clustering. But unlike the clusters, which are exclusive, communities can share nodes. Existing definitions we can divide into two categories. First, that are focused mostly on defining the borders of the communities, and the second one, which focus more on the inner structure of the community. Definitions focusing on the borders often use in and out community degrees of individual nodes. In community degree is the amount of edges that connects analyzed node with the rest of the nodes of the community. Out community degree, on the other hand, is the amount of edges that connect the analyzed node to the rest of the graph. The other group of definitions focusing on inner structure of the community often use highly cohesive structures like cliques for defining the community. In our case, we define community as a two-part structure consisting of core and surrounding. The core is highly cohesive structure that sets the base for the community, whereas surrounding is an extension of the core helping with the problems induced by the process of capturing the data. So our definition fits more into the second group. Now I would like to mention three approaches that can be found in the literature. First one is called local expansion. This is a seeded algorithm that randomly picks a node as a starting point for a community and then extends this community in a such way that it maximizes fitness function. Once it maximizes the community, it picks randomly new node that is not assigned yet and starts to create new community. The quality of result of this approach is dependent on the right selection of seed nodes. This approach has also two main problems. Firstly, it can easily get stuck in the local maximum. Secondly, it can create a communities containing big chains of nodes that have big diameter. The second approach is called clique percolation. It is a two-step process of detection of cliques of fixed size and then merging them together into the communities. The problematic part of this approach is to select the right size of the cliques. If small cliques are selected, we get a lot of communities with a big diameter. But if the large size of cliques is selected, we may not get any result. The third approach is called link clustering. This approach is based on the comparison of links. The main idea of this approach is that link is unique for the community. As such, we can search for clusters of links instead of overlapping communities. This approach has two parameters, core size and similarity threshold. This is important for later part of this presentation. The process of this approach consists of three steps. First, identifying clusters of similar edges, then enlarge these found clusters by an assigned neighborhood, and at the end, aggregating nodes associated with the clustered edges. So the approach transforms linked clusters into the node communities. Now let's take a look on our approach. We call this approach FIMSIM. It is a two-step approach that first finds cores of the communities and then it assigns the surrounding to found cores. The process of core detection is based on the task called frequent item set mining. For the selection of the surrounding, we use Similarity Search. Now let's take a look on the individual steps. First, core detection. As I mentioned in the overview, we use frequent item set mining for the core detection. Frequent item set mining, sometimes called market basket analysis, was proposed by Agrawal et al. It was used for detection of items bought together in the supermarket. The task is to analyze the database containing the sets of items and find the frequent subsets. Parameter data is often used as the notion of minimal support, which is provided by a user. Minimal support sets the threshold for how many times the subset must occur in the database to be marked as frequent. Now, if we represent our graph with a list of neighbors representation, we can view the graph as a database containing sets of neighboring nodes. Set of neighbors of the node can be used as the basket, and individual neighboring nodes can be used as the items. We can then get the collection of frequent sets by applying standard algorithms of frequent item set mining. This collection of frequent sets is a superset of cliques in the graph. The reason why the clique will be in the collection of frequent sets is because each member of the clique will contain whole clique in its list of neighbors representation. So this collection will contain all the cliques bigger than parameter data. For this research, we use standard algorithm FP-GROW. Once we obtain the collection of frequent sets, we have to do some core filtration. This is caused because the collection contains two types of undesired cores, the smaller than the data and sets that are less frequent compared to their size. Once we obtain cores, we can start to select the surrounding. First, let's talk about how we compare nodes and cores. For the comparison, we again use list of neighbors representation of the node. Because this is the set of individual nodes, we can compare it with the sets of nodes from the core. For the selection of the surrounding, we use distance function that leads to zero in two cases. First, it has zero distance in the case that all neighbors of the node V are members of the core C. In this case, node V is connected only to the core C and not to the rest of the graph, so this node should be part of the community. The second case, when the distance should be 0, is when the node B contains the whole core C in its list of neighbors. On the slide, you can see the proposed distance function we used for the experiments. It is possible to use standard metric functions for comparison of sets, but for example, Jakub coefficient penalizes nodes with a lot of neighbors. Now let's talk about the similarity search. For the selection of the surrounding, we use range query, where we compare core with the list of neighbors of individual nodes of the graph. Because we don't use metric function, the search is done by sequential scan. In the experiments, we compared each core with each node of the graph. This can be optimized by elimination of non-neighboring nodes from the comparison. In our approach, it is also possible to replace range query with KNN query. The benefit of using KNN query is that we can control the result size of the communities. Usage of KNN query brings several drawbacks. First, parameter k must be selected correctly. It can happen that when k is too small, smaller than the core size, not enough nodes from the core will be selected for aggregation. Secondly, if core is not part of the selection during aggregation, it will lead to elimination of the community. After we obtain results from similarity search, we aggregate them into the communities. In the post process, we check whether community also contains whole core. If not, the community is eliminated from the result. As a result, we get the collection of communities. Now we will look at the experiments. For the experiments, we use data we obtain from Konica Minolta. These are access logs to files. Each log contains 5 columns: date, user ID, action type, document ID, and document type. There is 6 action types: download, previewed, edit, uploaded, created, and item shared. The data were pseudonymized. The data contains 383,000 records in the form you can see in the example box. From the access log, we created a collaboration network. This network contains user-user interactions, which are based on access documents. First, we try to create collaboration network from all the action types. Unfortunately, resulting network was too homogeneous to find any communities in it. So we used only 3 action types which are associated with the creation process of the document. These are edit, uploaded, and created. The resulting network contains 128 users with an average degree of 8.5. On the right image, you can see major cluster of nodes. From the image, there were omitted several users which didn't collaborate with any other user. For the purpose of evaluating the quality of our results, we use 2 metrics. First one is called Modularity and was proposed by Girvan and Newman for the evaluation of clustering. The metrics compare the amount of in-group edges to the rest of the edges. This works well for the evaluation of the clusters because it prefers minimum of the edges going into the other groups. Unfortunately, it penalizes overlaps which are more dense than the borders without the overlaps. The metrics give a higher number for the better separation of the groups, and it can go up to 1 when the groups are totally disconnected one from each other. When the whole graph is assigned into one single community, the metric gives us 0. When the separation is really bad, the modularity can go up to -1/2. The modularity will start to have problems when more complex graph with more edges is evaluated. Once the separation is not so clear, it will try to propose division into two groups. But even for this division, it will give a low score because there is a lot of edges between these two groups. Once we introduce some overlap between these two groups, the score will drop rapidly. This is because overlapping node will decrease score twice, once in each evaluation of group. For this reason, we adopted second metric called overlapping modularity. This metric was proposed by Chen et al. And uses the same process of evaluating nodes. The difference is that nodes are weighted based on the amount of communities it participates in. Even though this metric is trying to account for the overlaps, it still prefers communities without overlaps. In the experiments, we compared our approach FIMSIM with Debeling clustering. We choose this method for two reasons. First, it shares parameter space, and secondly, the shape of the resulting communities is more similar than in other two approaches. On the slide, you can see quality comparison of the results of Debeling clustering and FIMSIM. Although both methods share the parameter space, parameters are not overlapping 100%. For this reason, it is important to compare peaks of the lines instead of the whole lines. In the line chart, there are two different kinds of lines. The whole lines for overlapping modularity and dashed lines for normal modularity. In both cases, the results of our algorithm gets a better score. It is also important to look at the shape of the lines. Our algorithm gets score 0 until the point when it returns some results. But after that, it spikes into the most quality results. Whereas quality of results from debugging clusterings is oscillating. This starts to be important when we take time into the account. When we look at this time efficiency comparison, we can see that our approach will finish quickly when there are no results. Debugging clustering, on the other hand, uh, takes a lot of time even when no result is provided. This behavior of our algorithm can be used for a simple search of parameter space for quality results. When we analyze the network data, we can start with high number for minimal core size. Even though that we will not get any communities as a result, the algorithm stops almost immediately. We can then lower the minimal core size parameter until the moment when we will get some results. In that moment, there is a high probability that we will get a result with a high quality. In this paper, we proposed algorithm based on frequent item set mining and similarity search. Frequent item set mining is used for core detection, whereas similarity search is used for assigning the surrounding to the cores. We tested our algorithms on the collaboration network provided by Konica Minolta. We compared our algorithm with Debeling clustering algorithm, and we outperformed Debeling clustering in both time efficiency and quality of the result. The big benefit of our approach is also the simplified process of parameter selection. In the future, there is needed more testing on different datasets, and there are some steps which can be optimized. This research has been supported by the Czech Science Foundation and was made in collaboration with Konica Minolta. Thank you for your attention, and I'm looking forward to any questions during live events.